Welcome to the Deep Dive, where we take a monumental stack of sources, articles, and research and distill the most surprising and essential nuggets of knowledge for you.
Today we are wrestling with a question that seems, deceptively simple on the surface, but it sits right at the very foundation of all science.
Yeah, how does reality organize itself? I mean, we all intuitively slice up the world into these neat compartments. You've got physics over here, chemistry here, biology, sociology, but what's the actual relationship between these layers? What connects them?
This is a deep dive not just into what science studies, but really how it studies it. We're exploring the philosophy and the actual practice of what are called levels of explanation.
And we have a fascinating collection of work here. We're drawing heavily from philosophers of physics, biology, and even mathematics to investigate the conditions under which a specific level of description, well, how it gains its own autonomy and its own explanatory power.
Yeah, that's it.
Our core mission here is to unpack a paradox that, and this is amazing, stumped even the great philosopher of mind, Jerry Fodor. He once declared himself utterly unable to answer it.
Right. And the conundrum is this. How do we explain high-level phenomena? I mean, why is it that when we talk about evolution or the stock market, or even something as simple as pouring a glass of water, we do not have to constantly go back to quantum field theory for every single explanation?
It seems like we should, right? If everything is made of particles. But we don't.
And that's the essential challenge. We assume the world is fundamentally physical, which means the higher level facts, the facts of chemistry or biology, they must depend in some way on the lower levels. That's the idea of dependence.
The facts of chemistry are fixed by the facts of physics.
Exactly. But if the higher levels depended entirely on the lower ones, they'd have no independence. Physics would be the only real science.
And everything else would just be what? Bookkeeping.
Sort of, yeah. So we're looking for that sweet spot. We're searching for the criteria for emergence, the rules that allow a level to be viable, useful, and robust enough to stand on its own without us needing to know every single micro detail.
We're looking for the criteria that make a scientific level, as the source material puts it, worth having.
And the answers, as we'll see, are surprisingly technical. They draw evidence from the mathematics of coupled oscillators, the intricacies of motor control in biology, and even the high-energy physics of effective field theories.
This should be fun. This deep dive should fundamentally change the way you view the syllabus of your next college course. Okay, let's unpack this from the ground up. When we talk about these levels, physics, chemistry, biology, are we just talking about how we organize our knowledge? Are they just convenient labels for our books and departments?
That's the epistemic view.
Right, the epistemic view. Or are we making a claim about the actual, real structure of the world, the ontic view?
That's the classic distinction. And while, it's a valid distinction to make, the philosophical argument really leans heavily toward a correspondence between the two. The argument against it just being pure convenience is, well, it's pretty compelling.
Walk us through that. Why isn't it just a useful filing system for us?
Okay, so imagine if the levels were just arbitrary ways we chose to describe the world. Say, we group all phenomena with hydrogen atoms into one department and all phenomena involving, large animals into another.
That sounds a bit random.
It is. And if that were the case, it would be baffling that this arbitrary system allows for such incredibly successful prediction and explanation. I mean, why does focusing on genes and proteins give us such profound insights into heritability if the real explanation is infinitely more complex, lying only in the quantum dynamics of every single particle in the organism?
So you're saying if our level differentiated approach works so well, it suggests we're not just making it up, we're carving nature at its joints.
Exactly. Our ability to isolate phenomena and generalize about them so successfully, it suggests that reality itself has a corresponding system of ontological levels, a system where these high-level structures maintain a certain real independence.
If that weren't true.
To assume otherwise, that our scientific setup is just human convenience that somehow, magically, grants us all this explanatory power, well, one source calls it a kind of miracle. It would require more faith than explanation.
Okay, so the levels are real. They must be connected. What's the rule that binds a higher level, like chemistry, to the lower level, like physics?
The foundational constraint, the absolute bare minimum you need, is a concept called supervenience.
Supervenience.
The idea is that a higher level property cannot change without a change in the lower level properties that it, depends on.
Let's ground that with an example. If I have a digital photograph on my computer screen, the image itself, That's the high-level thing.
Right, that's a high-level property.
And it supervenes on the state of all the individual pixels, the lower level.
That is a perfect analogy. You literally cannot change the color or texture of that image without changing the underlying binary code and the physical state of those tiny illuminated pixels.
So if a butterfly changes color, that's a biological fact changing.
And that means you must have changed some underlying physical facts, even if it's just the arrangement of pigment molecules on its wings. There is no biological change without a physical change.
That sounds like a really powerful constraint. But it also sounds like it brings us right back to our original problem. If all the higher facts are fixed by the lower facts, how do we avoid the conclusion that physics is the only real science?
This is where it gets subtle. We have to emphasize that supervenience gives you a partial, not necessarily total ordering. It prevents arbitrary changes, but it doesn't force a strict linear hierarchy.
What do you mean by partial ordering?
Well, think about it like this. Levels like biology and geology, they both supervene on physics. They both depend on physical facts being true for them to exist.
That makes sense.
But is biology higher than geology, or is geology higher than biology?
Neither, really. They study completely different kinds of things. Life versus rocks.
Precisely. Neither is strictly higher than the other in some neat compositional stack. They're non-comparable in that vertical sense, even though they both depend on physics. And this is the key point. While reducibility implies supervenience, the reverse isn't true.
Ah, so you can have supervenience without being able to just translate biology into physics.
Exactly. Because many important properties and even possibilities are often level relative.
Level relative. That sounds a little like a philosophical get-out-of-jail-free card. If a property is real, shouldn't it be real at every level?
Not when you're talking about dynamic properties like, say, determinism. This is a crucial area where the levels don't mesh perfectly. Consider a box of gas. At the micro level, the microphysics, the interactions of every single particle follow precise deterministic rules. If you knew all the initial conditions, you could, in theory, predict every single collision forever.
Right, it's a clockwork system.
But when you coarse-grain that information, when you step back and look at the system at the macro level, the one described by statistical mechanics, the system is best described as indeterministic or probabilistic. We talk about the probability of finding a particle somewhere, or the likelihood of a temperature change.
So whether the system is deterministic or not depends entirely on the level of description we're using.
That's the key insight. The system hasn't changed its fundamental nature, but the predictive and descriptive tools available at that macro level, they only allow for probabilistic laws. It reveals a level relative indeterminism that is perfectly real and useful for that domain. And this idea has really profound consequences for the question of human agency.
The free will debate. The classic challenge. If physics is deterministic, then our choices are just the inevitable output of physical laws unfolding from the Big Bang.
And that challenge, which is often formalized in things like Van Inwagen's consequence argument, is often guilty of conflating the physical and the agential levels. It confuses different types of possibility.
How does distinguishing the levels solve that? Because I can hear a listener saying, look, call it what you want, but if the atoms in my brain can only follow one path, my feeling of choice is just an illusion.
That's the exact skepticism we have to address. The solution is recognizing that each level is endowed with its own distinct modal notions, its own concepts of possibility and necessity. The possibility of doing otherwise is what we call agential possibility.
Agential possibility.
Yes, it's a concept that exists at the level of agency, and it's defined by the psychological and cognitive constraints we face. So we can say a choice is open to me, that it's agentially possible, even if the underlying physical trajectory is singular.
Because the vocabulary of physics doesn't even have words like choice or desire or reason.
Exactly. The low-level description can tell you everything about particle movement, but it cannot express the concepts you need to even talk about agency. So if you try to mix them and say something like, conditional on the physical microstate, it is agentially impossible for me to act otherwise, that statement is just incoherent. It's a category error. You're mixing two vocabularies that aren't directly translatable.
So by partitioning the world into levels, we're also partitioning the very nature of what's possible within those levels.
You are.
Okay, that establishes that levels have their own descriptive space.
Yeah.
But even the physical level, the supposedly complete picture, seems to leave something out. Let's talk about the most fine-grained level of all, indexical and first-personal facts.
This is where we move beyond the third-person world of physical facts and into subjective experience. David Lewis had this fantastic thought experiment with the two gods.
Yeah.
Imagine two ancient gods standing outside of space and time. They possess complete third-personal, non-indexical knowledge of the entire universe. Every physical fact, every historical event, every particle interaction, ad infinitum. They know everything there is to know objectively.
So they have total omniscience of the universe's state.
But Lewis points out neither God knows which of the two he is. God Alpha knows all the facts about the universe. God Beta knows all the facts about the universe. They know everything, yet they're still ignorant. They don't know their own location, who they are, or what time it is now.
That's really compelling. So the objective, non-indexical facts, the kind of stuff science usually provides, they underdetermine the subjective indexical facts, the facts about now or here or I.
We can model this. The non-indexical level corresponds to an ordinary set of possible worlds. Let's call it omega. But the indexical level corresponds to a set of centered worlds. An ordered pair of a world and a center, which points to a specific location or moment in that world.
So the combination of the world and the center is a much richer description than just the world omega alone.
Yes. And since you can have different centers, CC1 and CETA2, combined with the exact same body of non-indexical facts, omega, it means the indexical facts clearly do not supervene on the non-indexical ones. The indexical level is fundamentally lower, more richly specified.
And connecting this back to consciousness.
Yeah.
This seems to give us a structural reason for the hard problem of consciousness.
It does. We can amend the model to capture first-personal experience using what's called a first-personally centered world. This is the ordinary world, plus a locus of subjectivity, let's call it pi. This combination determines all the third-personal facts and all the first-personal facts, what it is like for a conscious subject to be experiencing the world.
Which would make the first-personally centered level the lowest, most specific level of all.
Correct. And this structure, it vindicates the claim that facts about first-personal experience do not supervene on ordinary physical facts, the facts you can access from a purely third-person view.
So the hard problem stems from a mismatch.
It's a fundamental mismatch. Science is typically designed to give third-personal explanations of third-personal phenomena. But the thing we're trying to explain, conscious experience, is located at the first-personally centered level. It's structurally richer than the third-personal level where we're looking for the explanation.
We're trying to explain a centered fact using only non-centered information.
And that may be why it feels so intractable.
That's a powerful idea. The levels define the very structure of the facts we're trying to explain. But if the world is structured this way, like a tower of supervening facts, we often assume it stacks up neatly. Let's move on to some critiques of this neat, layered world and the assumption of what's called localism. Okay, so traditional philosophical models, they tend to assume that these levels are arranged vertically, right? Based from metaphysical determination. Things like composition, realization, supervenience. If I want to explain why salt dissolves, I look at its local atomic structure.
Exactly. Or if you want to explain why a bird flies, you look at its muscles and feathers. This is what you called localism about explanation.
Right.
Localism argues that phenomena are explained by their immediate causes or their composing parts. And, this works really well for simple physical systems, but it runs into serious trouble when you try to apply it across the board. It challenges both traditional reductionism and the classic anti-reductionist views.
So why does localism fail in real scientific practice? What's the problem?
The problem is that scientific counter-evidence shows that phenomena are regularly determined by large-scale distant factors and structural influences, not just what's locally composing them. Think about sociology, for instance. If you want to explain disparities in opportunity, a localist approach would focus on individual choices or, very proximate causes.
But the sources suggest we have to look much wider than that.
Absolutely. To mitigate systemic issues like racism or economic immobility, you have to renovate entire social systems, legal structures, market designs. It's the large-scale structural patterns, the very geometry of the social world that determines the outcome, not just the local facts about the individuals inside it.
It's not just about the person, it's about the system they're in.
Precisely. Or take ecology. We used to think that population abundance was determined locally by predator-prey dynamics in one little area, but we now recognize it's shaped globally by huge processes like the evolution of specialists versus generalists across vast geographical ranges.
Okay, so if explanations aren't always vertical, not always about composition or immediate causes, how should we understand the relationship between different sciences when they're studying the same outcome?
They're related, but often horizontally. Different fields looking at the same phenomenon often identify factors that have no special metaphysical dependence relationship to one another. They are separate, non-composing, horizontal influences.
Give us an example where we can see this horizontal approach in action, where the factors are clearly distinct.
Sure. Let's consider the phenomenon of heightened aggression in an organism. A neuroscientist might explain this by identifying specific neural structures, the amygdala, and its firing patterns.
Okay, the brain explanation.
A molecular geneticist might point to certain genes associated with hormone regulation.
The genetic explanation.
And a sociologist might point to early childhood exposure to violence or chronic environmental stress.
The social explanation. So you have three valid simultaneous explanations.
They are. But here's the thing. The genes don't compose or realize the neural structure in the same way that atoms compose a molecule. And the social influences are completely separate factors acting on the organism at a totally different scale.
So they're not in a neat vertical stack, they're parallel lines of influence.
Exactly. They're distinct causal pathways that all converge on the same high-level outcome. The sciences are attending to different kinds of factors at different scales, not just describing the same local thing with different levels of granularity.
That really seems to push us towards something called explanatory pluralism, the idea that you need multiple non-competing explanations to get the full picture.
It does, and the scarlet ibis is a beautiful biological illustration of this. The ibis has that intensely bright pink coloration. We have multiple totally accepted explanations for this one feature.
Okay.
One explanation focuses on carotenoid metabolism, let's call it X. It's about the specific enzymes and processes needed to break down carotenoid pigments from the bird's food.
The biochemical story.
Another focuses on a specific carotenoid carrier protein, let's call it Y, that physically transports the pigment to the feathers.
The structural story.
And a third focuses on mate attraction and sexual selection, Z, where the vibrancy of the color serves as a crucial signal for reproduction.
The evolutionary story. And nobody would argue that the metabolism causes the sexual selection dynamic or vice versa.
Of course not. They are independent influences. The choice for the biologist isn't how fine-grained to describe the local atoms. The choice is which kinds of factors at what scales to pay attention to, metabolic, structural, or evolutionary. The traditional reductionist framework, which is obsessed with vertical composition, it just fundamentally misses the importance of these large-scale and distal influences. Localism about explanation fails to capture huge swaths of real science.
But if localism fails, does that mean reductionism is just completely doomed? Is there any version of reduction that survives this critique?
Yes, there is. We have to pivot away from the idea of grand theory reduction, the dream of deriving all of biology from physics. Instead, we focus on localized reductive explanation. Philosophers like Alexander Franklin argue that the goal isn't universal derivation, but to provide these piecemeal, bottom-up explanations for the stability of high-level features.
That's a critical distinction. We're not trying to replace biology with physics. We're trying to explain why the high-level models used in biology actually work so well.
Precisely. A successful reductive explanation details the specific, smaller-scale structures and processes that justify discarding all the other degrees of freedom when you build your macro-level model. It explains the robustness of the higher-level description. Think of dislocations in crystals.
Dislocations, okay, those are the imperfections, the irregularities that move through the atomic lattice of a solid and determine its strength.
Right. A dislocation is a mesoscale structure.
Yeah.
It's above the atomic level but below the macroscopic level. And it's a stable structure. Its stability is explained from the bottom up by the underlying atomic lattice and the stable trade-off between two kinds of energy.
Which are?
Misfit energy, that's the energy cost of the atoms being out of alignment. And elastic energy, which is the energy stored in the crystal when it tries to spring back and correct that misalignment.
So the dislocation is a stable configuration because it's just energetically favorable for the lattice to contain this fault rather than trying to fix it completely.
Yes. And the high-level mesoscale description, the description of the dislocation's width and its movement, is effective because its overall structure is dominated by only a few crucial smaller-scale details. In this case, it's the ratio of the interlayer distance to something called the Berger's vector.
Yeah, that's it.
That's the key detail. That specific low-level ratio makes the mesoscale description robust against all the other countless micro-details we could potentially track.
So this sounds like reduction as a mechanism for justification, not elimination. Reduction justifies why a specific high-level model one that ignores 99% of the micro details, is still reliable in its own localized context.
It's the bottom-up explanation for the existence of an autonomous top-down model. And this kind of localized reduction is absolutely essential for understanding what makes a level useful, which brings us to the formal criteria for a level worth having.
Okay, so if we accept that reduction can justify this localized stability, we're still left with the core puzzle. Why isn't the entire universe just fundamental physics? What makes chemistry or engineering or climate science worth having and not just, convenient but cheap levels of mere description?
We need two primary ingredients for a robust autonomous level: robustness, autonomy, and novelty. Robustness is the answer to why fundamental physics doesn't matter more, and novelty is the answer to why there is anything other than fundamental physics.
Let's nail down robustness first. What does that mean in this context?
Robustness is the property of a system that allows it to remain stable or unchanged under certain kinds of perturbations. For example, biological systems are robust because they maintain homeostasis even when they're challenged by minor disease or shifts in the environment.
They hold steady.
Right. And in physics, we talk about the thermodynamic limit. This is where a phenomenon like pressure in a gas becomes independent of the exact number of particles as long as that number is really, really large. The pressure is robust because the statistical average screens off all the variations in the individual particle movements.
And autonomy, then, is the formal name for that screening off process.
Yes. Autonomy, formally, happens when a high-level fact, let's call it macrofact A, screens off the relevance of a low-level fact, a microfact B, conditional on another high-level fact, macrofact B.
Okay, that's a bit dense in simple language.
In simple language, it means that the microphysical details might matter for a phenomenon, but they don't matter for our prediction of it once we've already established the macroscopic context. We can discard the micro details because their influence is statistically washed out.
Okay, that gives us a shortcut. That gives us robustness. But shortcuts don't give us genuinely new science. That's where novelty comes in.
Novelty is what justifies a new science, and it comes from making specific changes of variable that reveal dependencies that were completely opaque or hidden at the lower level. We're transforming the mathematical description in a way that reveals a real, simplified truth about the world that was impossible to see before.
Let's see this in action with the coupled oscillators example from the sources.
Okay, imagine you have two masses connected by two springs. If you try to model their motion using their original spatial coordinates, 6/1 and 6 2-tolars, the equations of motion are just a mess. They're complex, they're linked, they're notoriously difficult to solve. They don't give you any simple, intuitive understanding of what the system is doing.
They're coupled second-order differential equations. It's a nightmare.
It completely hides the structure. But if you perform a change of variable, if you transform 6/1 and 6/2 into what are called normal modes, one variable that represents the motion of the center of mass of the whole system, and the other that represents the distance between the masses, the equations immediately uncouple. They become two simple, independent, harmonic oscillators.
So just by changing your perspective, your variables, you simplify the math drastically.
But the novelty is much more than just mathematical convenience. If you ask the question, what determines the spring compression between the two masses? The normal mode transformation reveals that the spring compression depends only on the distance mode, data to a 2. It is completely irrelevant to the center of mass mode.
Wow.
That's a fact about the world, a real dependency that was utterly invisible in the original 6 by$2 description.
So the new level, the one defined by the normal mode variables, isn't just a convenient abstraction. It actually captures a genuine, novel, causal dependency that the fundamental physics had obscured under a wave of messy detail.
Exactly. A level is worth having when its variables are both robust and they reveal novel, real dependencies. Now, what's fascinating is that physics itself provides the most systematic and controlled method for deriving this kind of level structure, effective field theories, or EFTs.
The idea that our most fundamental theory, quantum field theory, inherently sanctions the existence of these lower energy, non-fundamental theories.
This is the systematic explanation for why physicists can study their own domain without having to solve the grand unified theory first. EFTs define the physics below a certain energy cutoff, which is denoted as lambda. They systematically describe phenomena at larger scales, which means lower energies, by mathematically integrating out the high-energy, small-scale details.
Explain integrating out in real terms. Is that just a fancy way of saying we're throwing away the details we don't care about?
It's fundamentally different from a convenient lie or a mere approximation. When you integrate out the underlying high-energy physics, the mathematical process itself generates a new infinite series of terms for the low-energy fields. These new terms account for the effects of the fundamental physics you removed.
An infinite series still sounds pretty complicated.
This is the genius of the autonomy mechanism that seems to be built into nature. Every new term that gets generated by integrating out the high-energy physics is systematically suppressed by a factor of lambda. Here, $m is the low-energy scale you're examining, and lambda is the high-energy cutoff. And since $m is always small compared to the large lambda, that ratio is always much, much less than 1.
So when you raise that tiny fraction to a high power, the whole term just rapidly approaches zero.
Precisely. At low energies, the terms in the series with a high value of $0 become negligible. And since all prediction in physics is done to a finite degree of empirical accuracy, you only need to incorporate a finite number of terms, often just the first 2 or 3 into your calculation. The rest are smaller than the limits of our experimental equipment.
So the fundamental physics is technically still involved, but its influence is systematically minimized by the energy cutoff. It's screened off by the math itself.
It's not just an approximation. It's a systematic explanation, confirmed by our most successful modern theories, of why nature comes sequestered into different regimes. The EFT framework guarantees the autonomy and robustness of non-fundamental theories, explaining why, for example, a condensed matter physicist can operate effectively without ever worrying about the specifics of quantum gravity.
That's a powerful insight. The internal structure of physics itself dictates the structure of scientific knowledge. It justifies the disciplinary boundaries we see every day, systematically. We've seen how physics provides these vertical layers, sanctioned by its own mathematics. But when we move to biology, the complexity just explodes. When biologists talk about levels, are they applying one uniform structure, or do they use different kinds of levels depending on what they're trying to explain?
They employ distinct, locally defined level structures that are designed to solve different problems. The sources detail 2 primary types in biology: mechanistic compositional levels and control causal levels, and they're defined by how the parts relate to the whole.
Okay, let's start with mechanistic levels. What makes them compositional?
Mechanistic levels are defined by decomposition into components, entities, and their activities that together generate a phenomenon. This is the classic part-whole relationship. The mechanism is at a higher level and its parts are at a lower level. But crucially, the organized activity of the components constitutes the operation of the mechanism. They don't cause it.
Help us distinguish constitution from causation in this context. That sounds tricky.
Okay, take muscle contraction. The whole mechanism is the contracting muscle fiber. The organized activity of its components, like the myosin heads binding to actin, powered by the limb-Taylor cycle. That complex dance just is the operation of the muscle mechanism.
So the myosin heads don't cause the muscle to contract.
Their structured movements are the contraction. If we claim they were separate causes, we'd run into the philosophical problem of overdetermination, where you'd have the whole mechanism and its parts both independently causing the exact same effect. It's redundant.
That makes perfect sense. The parts acting together are the activity we're describing.
Exactly. This compositional relationship helps us avoid a lot of metaphysical headaches. But because different researchers might decompose the same system in different ways, some looking at molecular components, others at cellular ones, these mechanistic levels are only locally defined. They don't automatically form a grand general stratification that spans all of biology.
So mechanistic levels help us understand what a phenomena is made of. How do control levels differ from that?
Control levels describe a causal relationship. A control mechanism acts on and modifies the behavior of a separate controlled mechanism. And this system is often highly nonlinear, which is why control levels are typically hierarchical, not strictly hierarchical.
Hierarchical, meaning control isn't exercised top-down by a single CEO, it's distributed across the system.
Precisely. We often have this default assumption of a hierarchical organization, the cerebral cortex being the CEO of the nervous system. But research on motor control, for example, shows a much messier, more distributed picture.
How so?
The spinal cord itself contains what are called central pattern generators, or CPGs, that can produce basic rhythmic activities like walking or breathing, completely independent of brain input. These CPGs integrate multiple causal inputs: feedback from the senses, input from the midbrain, and so on.
So the control is layered, but it's not a simple chain of commands.
It's more like a network. For instance, subcortical areas like the basal ganglia are crucial for selecting and initiating complex actions. They essentially adjudicate between conflicting potential actions that are being proposed by different parts of the brain. The control is totally distributed.
And it's not always direct neuron-to-neuron firing.
Not at all. We also see control exerted by things like neuromodulators, dopamine, noradrenaline. These don't cause individual neurons to fire in a predictable way. They diffuse through the fluid around cells and alter the metabolism of those cells, modifying how their receptors respond to other signals.
So they're not dictating a specific action. They're setting the context or the agenda for all the synaptic processing that follows.
Exactly. Their action is explicitly causal, defining a control level where one system modifies the sensitivity and behavior of a separate controlled system. So biology really needs both. Compositional levels to understand what things are made of, and causal levels to understand how they control each other.
Let's shift to cognitive science then, where David Marr famously tried to impose a very neat tripartite level structure to understand the brain, using the analogy of a cash register.
Marr's framework was explicitly designed as an anti-reductionist strategy. He argued that trying to understand complex systems just by extrapolating from the properties of its elementary components was, in his words, futility. He used that analogy of designing a cash register to define 3 distinct levels of abstraction that are necessary for any analysis.
And what are these 3 famous levels?
First, you have the computational level. This is the what and why. It defines the goal and the logic, independent of how it's achieved, like the rules of arithmetic for a cash register. Second, the algorithmic representational level. This is the how. It details the specific steps, the data structures used, the format of the input and output, like choosing to use Arabic numerals instead of Roman ones.
And third?
The implementation level. This is the physical substrate, the hardware. The nuts and bolts, the circuits, the transistors, or in the brain, the neurons.
And this approach has been incredibly influential because it neatly separates the software from the hardware.
Right, and it provides the justification for disciplinary autonomy in cognitive science. It relies heavily on Herbert Simon's argument about the architecture of complexity. Simon argued that complex, evolved systems must be hierarchically composed of relatively independent subsystems. He called it near decomposability.
Why must complex systems be like that? Why must they be nearly decomposable?
Because if a complex system was a tightly coupled interdependent mess, where changing one tiny component required you to recalculate the entire system, evolution would be vanishingly improbable. Complexity can only evolve through local modification of relatively encapsulated subsystems.
Which allows the higher levels to abstract away from the implementation details.
Exactly. You don't need to know the molecular mechanics of a transistor to understand the Python code that's running on it.
But the brain is so much more complex than a cash register. How robust is this analogy, really?
That's where the skepticism comes in. Critics argue that the brain might exhibit really high-density, cross-level interactions that fundamentally violate that clean independence. Furthermore, the brain exhibits something called deep degeneracy.
Degeneracy.
It means that different structural components can perform the same function, and more importantly, that biological machineries are often developed for a multiplicity of functions, not just the single optimized function we might assign to a cognitive module.
So the brain isn't optimized like a machine designed by a rational engineer. It's more like a Swiss Army knife that's been tinkered with for a billion years.
That's a great way to put it. And that contradiction between the expected modularity of Simon's artifact analogy and the observed, messy, cross-functional nature of biology. It suggests that while Marr's framework is a powerful descriptive tool, we shouldn't assume the brain actually adheres to that neat hierarchical blueprint in reality. The levels might overlap and blur far more than the analogy suggests.
We've established that high-level sciences need autonomy, and they often get it through abstraction or clever change of variables. But now we have to address the most difficult challenge: defending the idea that these high-level properties actually do causal work. I mean, if the physical level is causally closed, if every physical event has a sufficient physical cause, where does higher-level causation even fit in?
This requires us to defend irreducible downward causation, the causal influence of higher-level properties on lower-level ones, but in a way that doesn't violate physical closure or result in that overdetermination problem we talked about.
And we can actually see this in action, even in fundamental physics, specifically in how forces compose.
Yes. Let's use the vector composition example from the sources. Take 2 charged particles, Dulé and Tullers, positioned near some point in space, Let's call it $6. To explain the direction and magnitude of the resulting electric field at $0.6, you need the basic properties, the charges of the particles, and their spatial relations.
Okay, that's standard physics.
But calculating the final resultant vector dollar requires you to appeal to the geometric structure formed by the particles relative to that $0.6.
We add the individual force vectors together head to tail.
Yes, but the final explanation hinges on that geometric relationship. The fact that the fields from kilo to $2 might point in the same direction at x, or point perpendicular to each other, that is the geometric structure, and that structural property is what dictates how you do the calculation.
But wait, isn't that geometric structure ultimately reducible to just the specific coordinates of the particles?
While the structure is grounded in those basic physical properties, the geometric structure itself is multiply realizable. Many different combinations of particle charges and locations could result in the exact same geometric property, for instance, the fields being exactly perpendicular.
Oh.
So if you want to explain why the total field points where it does, you have to appeal to that geometric property, and that property isn't unique to any single set of microphysical facts.
So the geometric property is a kind of novelty that you can't eliminate without losing explanatory force. But what is its causal role? How does it do anything?
The higher-level geometric properties exert a novel causal role by acting as manifestation conditions on the causal powers of the basic physical properties. The fundamental powers of the charged particles are still doing all the work, but the geometric structure determines how those powers manifest, how they combine, and what the final outcome is.
So the geometry doesn't compete with the charge, it doesn't add a new force, it constrains or directs the outcome of the existing forces.
That's the key. And this secures the autonomy of sciences like chemistry, which classify molecules based on geometric features: linear, planar, tetrahedral. Molecular geometry is a multiply realizable geometric property that conditions the manifestation of the underlying quantum forces. This allows chemistry to abstract away from specific electron configurations and focus purely on structure. This is downward causation that fully respects physical closure.
That helps explain how structural properties can be causally relevant. Now let's go back to the success of high-level models, like in economics or ecology, that deliberately ignore all this micro-detail. How can a deterministic low-level universe produce reliable high-level laws that are fundamentally ignorant of that determinism?
This is explained by a pervasive scientific mechanism called semi-detachment. It means there is a kind of stochastic or random independence between variables at different levels. And this is widespread because the sheer complexity and disorder of the low-level events ensures stability at the high level. The low-level details effectively cancel or balance one another out.
Can you give us that statistical mechanics analogy again?
Sure. Think of the movement of a massive number of molecules in a gas. They are all colliding deterministically, but their individual trajectories are just way too complex to track. The collective outcome, however, is orderly. The very disorder of the outcomes, the countless random directions and speeds, ensures a stable, high-level thermodynamic behavior, like consistent pressure or temperature.
It's like a coin toss. Each individual toss is random, but over 1,000 tosses, it settles to a very predictable average frequency of 50%.
Exactly. The high-level behavior becomes stable because the variability at the micro-level averages out. Now, consider the Lotka-Volterra model, which describes the cycling of predator and prey populations. This is a high-level model. It ignores the individual positions, the health, or even the genetic makeup of the individual animals.
And yet the model works pretty well.
It works precisely because the dynamics are driven by numerous low-level events: births, deaths, pounces, illnesses, whose variability averages out over time. The high-level parameters like birth rate and death rate are semi-detached from the micro-details. The individual events cancel each other out,
which allows the high-level model to accurately predict the qualitative stability of the whole system, even though the underlying low-level system is deterministic through and through.
The high-level model is reliable, not despite ignoring the micro-details, but in many cases because it ignores them. Ignoring all that noise allows the signal of the average behavior to become clear and robust.
So this canceling out approach is a principal explanatory tool for the viability of high-level modeling across all areas of science.
It is. It demonstrates that the robustness and autonomy of these levels are based on objective, real-world properties of the systems themselves.
We've spent this time establishing that the levels are autonomous, complex, and sometimes pretty messy. But how do we ensure they all fit together without contradicting one another? If chemistry has its own laws, and physics has its own laws. How do we coordinate the laws of physics, biology, and economics to form one coherent scientific view of the world?
This is the scientific coordination problem, and it forces us to ask a really fundamental question. Where does the lawhood, the law-like force of all these special science generalizations actually come from?
What are the main competing philosophical camps on this?
We have three primary perspectives. First, there's imperialism. This view claims that lawhood derives wholly from fundamental physics. The laws of chemistry are just highly complex, derived instances of the laws of physics.
What's the major flaw in that view?
Well, imperialism struggles because the laws of fundamental physics are typically exceptionless and temporally symmetric. They look the same, running forward or backward in time. But special science laws, like in biology or economics, are full of exceptions, and they are overwhelmingly temporally asymmetric. A predator population collapse looks very different from its rise.
So imperialism fails to capture the real character of special science laws.
Right. The second camp is anarchism. This claims that laws are determined independently within each science. Biology determines what counts as a law for biology, economics for economics, and so on.
That just sounds like intellectual chaos.
It does. It fails because it can't account for the mutual constraint between sciences. You can't have a law of biology that fundamentally contradicts a known law of chemistry. And it fails to explain the asymmetry where physics explains the existence of the complexity, the atoms and life, required for the other laws to even exist in the first place.
So we need a third way that respects autonomy, but insists on some kind of overall coherence.
That leads to the democratic view of laws. This approach, which is often rooted in a modern Humean philosophy, argues that lawhood is determined by adopting the set of generalizations from all the sciences that provides the best system summary of all known facts.
So we're optimizing the entire system of knowledge itself. What defines the best system?
It's judged by maximizing three key virtues at the same time. Accuracy, it has to match the facts. Comprehensiveness, it has to cover the largest possible domain. And repeatability. It has to successfully predict future instances.
And how does that play out?
Well, the laws of physics are extremely accurate and comprehensive, but the laws of biology are often highly repeatable and provide unique insights into specific, complex facts. The best system combines them all, finding the maximal balance of all those virtues together.
And this would explain why special science laws are still considered laws, even though they have exceptions.
Exactly. This democratic approach accounts for the counterfactual robustness of special science laws. For example, the law of supply and demand would probably still hold even if the fundamental forces of the universe were slightly different, as long as you still had a society that engaged in organized exchange.
The law is robust against microphysical changes.
Yes. And the democratic view also explains why special science laws have exceptions that require you to reference concepts outside the domain of that science. To explain a thermodynamic exception, you have to talk about particle momenta, which is a concept from outside classic thermodynamics. The whole system works together.
That provides a unified metaphysical backing for this entire layered scientific enterprise. Now, let's revisit the idea of explanation itself, which seems to be highly dependent on context, regardless of the law. Let's talk about that famous example that Molière satirized. Opium has a dormitive virtue because it induces sleep.
Right. Traditionally, this is held up as the quintessential example of a bad circular explanation. But the sources provide a deep philosophical refinement. If dormitive virtue is just understood as a conceptual marker for a stable pattern of events, namely opium reliably induces sleep, then the explanation is often considered formally adequate.
Wait, formally adequate? It's still useless.
Exactly. The problem isn't one of metaphysical inadequacy. The problem is that the explanation is contextually inappropriate. It provides insufficient explanatory distance.
Okay, break that down.
There's a philosophical approach known as the contextualist, pluralist, and non-realist backing view, or CPN. It states that explanation relies on backing relations, causation, grounding, conceptual relations. If the explanation is just reporting a conceptual relation or a stable pattern, it displays insufficient explanatory distance for what the listener actually wants to know.
It's the difference between saying the bridge fell because it was not structurally sound and saying the bridge fell because the bolts holding the western truss sheared under a load exceeding 120% of its rated capacity due to an unaddressed material flaw. Both are true, but one gives me much more new information.
That's it exactly. The dormitive virtue explanation provides no new information beyond the original statement that opium makes you sleepy. It's logically fine, but it's pragmatically disastrous for a listener who is seeking knowledge of the mechanism, how it actually does the job. The negative verdict on the dormitive virtue case is driven by this pragmatic, contextual failure, not by some deep metaphysical flaw in the statement itself.
So a good explanation depends on the audience and what they already know. Does this contextual pluralism also apply to pure mathematics, where the concept of physical causation is totally absent?
Absolutely. Mathematics is a fascinating test case for this. Take Fermat's little theorem. If pi r is a prime number, then AP1 is congruent to $1, text mod, PP. This theorem is proven, but it has multiple fundamentally different proofs. One using number theory, one using group theory, and another using combinatorics, which is called the necklaces proof.
If they're all logically sound, are they all equally explanatory?
No, but the determination of which proof is more explanatory is intensely context-sensitive. It depends entirely on the epistemic interests of the mathematical community. The number theory proof is valued because it demonstrates that the result holds because of facts that are intrinsic to prime numbers and divisibility. It stays internal to the subject matter.
It shows why the numbers themselves demand this result.
Whereas the group theory proof is valued because it connects the theorem to these overarching structural patterns established by advanced logic. It relates it to the general structure of mathematical groups. It shows the result is necessary because of the fundamental rules of abstract algebra.
So if a mathematician is teaching a course on abstract structures, they'll prefer the group theory proof because it shows broad connectivity. But if they're teaching number theory, they'll prefer the number theory proof for its internal coherence.
Precisely. As the source material notes, this challenges the whole search for a single, unified account of mathematical explanation. Even in the most rigorous, abstract field we have, explanation is governed by the context and the interests of the community. It shows that explanatory pluralism is deeply rooted, regardless of whether causation is involved or not. Hashtag tag outro.
This has been an incredibly rich deep dive, and it's fundamentally clarified why science isn't just physics all the way up. We've established that levels are critical organizational tools, but they're layered in these complex ways. They can be compositional in mechanism parts constituting the whole.
Or they can be causal in control, where one mechanism modifies the behavior of another.
And we identified the objective sources of this level autonomy. First, mathematically, through things like effective field theories, which systematically screen off the high-energy details using energy cutoffs that are guaranteed by that Frame suppression.
And second, statistically, through semi-detachment, where the sheer disorder of all the low-level events just cancels out, providing stability and allowing for reliable, high-level models that are semi-detached from the micro-details.
So levels are worth having, not just because they're convenient shortcuts. They actually reveal novel dependencies. They show us real causal relationships that only come into focus when we choose the right higher-level variables, like the normal modes or the geometric structure that conditions causal powers.
The puzzle of why higher levels exist is really solved by understanding where this novelty and this robustness emerge from. And the ultimate coherence of this complex, layered scientific picture is maintained by that democratic view of laws. The idea that the laws across all sciences are ultimately determined by a single system that maximizes accuracy, comprehensiveness, and repeatability across the entire domain of facts.
Which leaves us with a final provocative thought for you, the listener, to mull over. If the organization of scientific knowledge is judged by its ability to define laws that maximize these explanatory virtues across all levels, and the autonomy of those laws is dictated by structural properties like multiplicity of realization or statistical cancellation,
then when we encounter crucial phenomena that currently defy our level organization, especially those driven by complex, non-local structural factors like the global forces that shape ecological or social behavior, should we just be looking to reform our existing disciplines, or should we be seeking a new scientific discipline entirely?
one whose entire founding mission is to define robust and novel structural laws that best summarize the facts we observe at these large structural scales, accepting that these laws may not be vertically constrained by composition or individual action.
Food for thought indeed. Thank you for joining us for this deep dive.